Hello everybody and welcome to this tutorial. In this video I'll show you how to use LDAK-KVIK on the UK Biobank Researcher Analysis platform. So in the next slides I'll demonstrate how to set up a connection to the UK Biobank Research Analysis platform, how to install LDAK-KVIK and how to extract some phenotype and genotype data, and then finally how to apply LDAK-KVIK on these data. So these are some of the prerequisites before running LDAK-KVIK. So we require firstly that you have access to these data, that you have also dispensed the bulk data, which contains the genotype data, for example. And then finally, you should have installed the DX toolkit on your computer because this is what we'll use to set up a connection to the UK Biobank Research Analysis platform. In this video, we'll be making use of the cloud workstation to set up a connection with the UK Biobank Research Analysis platform. And this is also described on the DNA Nexus website if you're looking for more details on how to work with this connection. But before we can start working with this type of connection, we should start with setting up an SSH key. And this will allow us to log into the UK Biobank Research Analysis platform remotely. So I'll just do this as well in my terminal. So dx ssh config. And in my case, I have already created a key earlier, so I'll just select 0 here, use the existing SSH pair. And once you have created this SSH key, you can start a connection to the workstation using the command described over here. So I am just going to copy this into my terminal. And then you see that I have launched a job. And this means that I'm currently setting up a cloud workstation connection using this job. And what I can do now is I can SSH into this job ID, which means that I'll SSH into the cloud workstation. So I can just select this job ID and do the XSSH job. And as you can see, um, the job is not ready to start yet, so it might take 1 or 2 minutes before this is set up. So we'll just wait now until this connection is set up, and then we'll continue from there. Okay, we have now set up our connection with the cloud workstation. However, we are not yet in the directory we wish to work in. So before we're able to set up our workspace, we need to run these two commands. So we need to unset the existing workspace and cd into another one. So I'm simply gonna copy this into my terminal window. And we are now in this environment. So you can see there's already some files that are in here, and I think it's safe to ignore these for now. So, okay, we've set up our connection to the using the cloud workstation with the UKB wrap. And yeah, our next step would be to download LDAK into this environment. There's many ways to do this. For example, we could use Docker or we could use wget. So when we would be using Docker, we would first download the GitHub repository using this command git clone, for example, and build it using Docker, which is already installed on the research analysis platform. So I could just show you how to do that by copying this into the terminal. So I'm just copying the commands that are also on the slides. And this should show you that it's loading these data. So this might take a couple of seconds. Okay. And from this point on, you could run something like Docker run LDAK, and then you can see that it has indeed loaded LDAK as a Docker image. One other way to do this is would be using wget. So we would get the latest version of LDAK from GitHub. And in that case, we would have like a direct Linux executable. So we could, for example, run this. And then you can see that this also works. So that's great. We have been able to download LDAK on two different ways in the cloud workstation. So yeah, both of these would work to apply LDAK-KVIK to the UK Biobank Research Analysis platform. Then the next steps would be to prepare the genotype and phenotype data. So note that this is also described on the LDAK-KVIK website, so you could also always go back there if you want to go through the steps again. So we use the dx extract datasets command to extract phenotype data from the UK Biobank Research Analysis platform. So once you've dispensed the data, you should have this app ID, which is different for everyone. So I'm just going to copy this in my terminal to show you what it looks like here. So I found that the list fields command is particularly useful to see all the information that's available in this data set. And we can, for example, grab on certain variables that we're interested in, for example, height. And then we can see that this is measured on multiple instances, and it has this identifier, for example, participant.p50 and then first instance. But yeah, in these slides, we're interested in bilirubin, so you could look this up. And then we find that there's also multiple instances for this. And in this particular example, we'll be using this one. So the first instance of the measurements of bilirubin, this has this identifier, which I've also included here in the example code. So we can use the dash fields flag to indicate which fields we would like to extract. So right here, we'd like to extract the identifier of the participants and then also the information of bilirubin. So I'm just going to copy this into the terminal. And then this might take a little while. It should be extracting our phenotype data. Okay, we can check if this is indeed loaded. So I'm just going to search for bilirubin. Yes, it's there. So we find the headers, that those were our identifiers, and then we've also see that yeah, most individuals have been phenotyped for bilirubin. And then similarly, we can extract principal components as covariates. So I've already written it down here, but you can again use the list fields to see where the principal components are stored. For now, I'm just going to copy this into the terminal. Oh, I see that there has been a typo. So let me just correct that. So I'm currently extracting the first 10 principal components. Of course, if you wish to include more covariates as sex or age, this is also possible. So you would simply look up the fields that are there. Okay, so let me check whether I have correctly loaded the data. This all looks good. So it's currently a comma separated file, and LDAK requires tab separated files. So we would first have to clean these data to make sure it's in the right format. And we also need to change the headers. For example, as we've seen before, we currently have these headers. For example, the participant IDs have header, have a wrong header that starts with participant, for example, and likewise for the principal components. So what we can do is we can use the set command to change these headers. And what we can also do is we can substitute these commas for tabs and also substitute missing values. So for example, a double comma with an NA value. So yeah, you could of course always also do this in R, but for now we're simply going to copy in these commands to clean the data. Okay, so we can double check whether the data is currently in the correct format. So we renamed these files data bilirubin lowers dash tab. So if we look at it, this looks like a nice tab separated file, and the same should hold for data PCs tab. This looks good. Okay, so, oh, whoops. Now that we have prepared our phenotype data and our covariates, we can prepare our genotype data. For this, it's possible to prepare imputed genotype data or to focus on directly genotype data. And if you wish to work with imputed genotype data, we do not recommend working with this cloud workstation because it might take a long time to download these data and to clean them. So instead, we recommend using the Swiss Army knife for this, and we've included some documentation on the LDAK-KVIK website to do this. During this tutorial, we'll just be working with directly genotype data for the purpose of demonstrating LDAK-KVIK. And it's possible to load these genotype data into the workstation using this command. So we use dx download and then specify the location of the genotype data on the research analysis platform. And this can take a couple of minutes. So I have already just run this, and I can also view them in my terminal window. So if we, for example, run LSL and try to grab these files, then we can see that we have chromosome-specific genotype data. For each chromosome, we have a BET, BIM, and FUMP file. And the easiest way to work with LDAK-KVIK is to first merge these genotype data files. So we can do that by first creating a list of the genotype data files. So this is what we do here in the first line. So for every chromosome, we add the name of the data to a list. And once we've done that, what we also do here in this tutorial is we're just going to randomly select 2,000 individuals from the genotype data, so that we will not work with the entire UK-Biobank data for now. We're just going to work with a reduced data set because this will just all work a bit faster, and yeah, because it's just for demonstration purposes. However, of course, everybody's free to work with the entire UK-Biobank. This will just simply take slightly longer to run. And then we can use LDAK to merge these genotype data using these commands, makepad to indicate that we're making a new genotype data file. We can specify the list of these chromosome-specific genotype data and indicate this keep flag, which means that we're just going to keep these 2,000 randomly selected individuals. So after running this, we'll be able to create this file UKB merged. And because this takes a little while to run, I've also just already done this during a break. So these are our output genotype files, and we can just quickly check whether these are indeed of the right size. So we can indeed see that there's 2,000 individuals in here, and they still are genotyped for all the directly genotyped SNPs. So this is approximately 800,000. And we'll continue to use these genotype data to run LDAK-KVIK. So in this tutorial, we'll be using the Linux executable, which we've downloaded earlier in the tutorial. However, it's of course also possible to use the Docker image for running LDAK-KVIK. So when we wish to run LDAK-KVIK step one, we first specify that we're using the Linux executable, and then we include this flag KVIK step one. Oh, apologies. And then we just specify the name of our output. So we'll just put KVIK here for now. So this will be the base name of our output files. We can then specify the genotype data that we're using. So we'll use this UK-Biobank merged file that we created in the previous slide. Specify our phenotype data and our covariates. And it's also optional to specify the number of threads that you wish to use for this analysis. This can speed up the analysis if multi-threading is available. So let me just quickly copy these into the terminal. We can see that LDAK is running right now. So it recognizes that there's 2,000 samples, for example. And then it starts with running KVIK step one. So during this step, LDAK computes leave one chromosome out polygenic risk scores, which are used as an offset in LDAK-KVIK step two. It also tests whether there's significant relatedness in the data. And if it does detect significant relatedness, it'll continue to estimate a scaling factor to ensure well-calibrated statistics. So as you can see now, LDAK-KVIK is in the training step of step one. So LDAK-KVIK used an elastic net to compute polygenic risk scores in step one. And during this training step, it estimates the best hyperparameters for tuning the elastic net. Okay, and we can now see that, yeah, we've been able to finish LDAK-KVIK step one. We're using a relatively small data set, only 2,000 samples. So in this case, it hasn't been able to construct very accurate leave one chromosome out scores. So if you were to include more individuals in the data, there's a higher chance of constructing yeah, more accurate polygenic scores. And after having run LDAK-KVIK step one, we can continue to run LDAK-KVIK step two, which is exactly the same arguments, except that you use LDAK-KVIK step two instead of one. So let me just copy that in. This should run fairly quickly. So as I said before, it'll just use the PRS that's computed in step one as an offset to compute to perform a linear regression in this case, because we're analyzing a quantitative phenotype, namely the bilirubin levels. And once this is completed, we can look at the output files we've created. So these are the output files for step one and step two. And then it's also possible to view the output summary statistics in the .assoc file here. So here assoc stands for association. We can do that by, for example, viewing like this. Oh, let me just expand this. So here we have the chromosome predictor and their association statistics. So in this case, we have not applied the SPA, the saddle point approximation. We recommend using this for binary traits to ensure well-calibrated statistics particularly when you're analyzing data with a high case control imbalance or when testing low frequency variants. So yeah, this was it. This was how to perform LDAK-KVIK on the UK Biobank research analysis platform. We've here used the Linux executable, but similarly, it's possible to use the Docker image to run LDAK. So I've just included the the commands right here. I'll also be posting the commands that I've used here in the comments or on GitHub, so that you're able to replicate these steps. I hope you found it useful, and I'll just add some final comments. So as I mentioned earlier about imputed time for analysis that do have a longer runtime, it may be preferable to run LDAK-KVIK using the Swiss Army knife instead of the cloud workstation, because we find that, yeah, when this does take a couple of hours, this is just a bit more practical. Particularly when analyzing imputed data, it's good to work with the Swiss Army knife. Finally, we do not recommend using all imputed data in LDAK-KVIK step 1 because this generally does not add a lot to the prediction accuracy of the leaf from chromosome out POS that are constructed. And in general, there'll be a lot of a high speed up when you're just focusing, for example, on common variants. So we include this also in the recommendation page on www.ldakvik.com. Thanks for listening, and if you do find any questions or bugs, please raise an issue on our LDAK GitHub page. That would be very useful. And yeah, thanks again. Bye bye.